Hi everyone. The title of my talk today is Fuzzing the MCU of Connected Vehicle for Security and Safety. First, let me introduce myself. My name is Chen, aka Flank Sky. You can call me Flanker. I am from Li Auto. Li Auto is a leader in China's new energy vehicle market. I'm currently a security inspector at Li Auto, responsible for the information security of in-vehicle domain controllers, including penetration testing, vulnerability mining, security architecture design, and so on. Before joining Li Auto, I worked at McuFuzz for 5 years, mainly in the field of bug hunting. I'm focused on Android and Linux kernel. Now I'm very interested in connected car security and hardware security, but I'm still a newcomer and hope to communicate with you guys. Today, I would like to introduce to you a tool called McuFuzz that we developed. The main function of this tool is to fuzz the MCU software of our domain controller. I will detail why we designed this tool and how it works. The first part is the background introduction. I will introduce the common attack methods and the EE architecture of the current smart car, and why we pay attention to the software security testing of MCU. It also includes difference between safety and security. The second part talks about the detailed design of the MCUFuzz and how to realize coverage-guided intelligent fuzz with the help of hardware debugger. The third part is a demo practice, which is a fuzzing of a CAN-bus application. The fourth part is a conclusion and the prospector of future works. The first part, the background introduction. In recent years, the EE architecture of smart cars has evolved rapidly, from the initial distributed EE architecture to the centralized EE architecture. Now we are in the second generation. The second generation is the functional domain architecture. In this architecture, the original single function controller is integrated into different domains according to their functional categories. For example, the power domain, the chassis domain, the body domain, intelligent driving domain, and the intelligent cockpit domain. The evolution of EE architecture also has a great impact on information security, both for the attackers and for the defenders. Let's take the current mainstream EE architecture as an example to talk about the common attack path. Let's first look at the functional division of each domain. In this picture, the DCU means domain control unit. You can see 3 DCUs here. The HMI, ADAS, powertrain, or chassis DCU. From the perspective of functional division, the most vulnerable to attack is definitely the HMI, because external connection links are all on the HMI system, such as Bluetooth, Wi-Fi, 5G, and so on. And the ESP, AEB, EPS related to vehicle control are all linked to the powertrain domain. Therefore, there is a possible attack link like this. Attack the HMI first, and then attack interacts with the powertrain domain. exploits the vulnerability of powertrain DCU and then sends arbitrary CAN command to control ESP, AEB, and so on. The MCU fuzz we propose is designed to test the MCU software on the DCU3, aka the powertrain and chassis domain, because the powertrain and chassis domain is the most critical domain controller in a modern car. So we can have a conclusion. The powertrain and the chassis domain are the hacker's ultimate goal, and its information security and functional safety critical system. Just now we mentioned functional safety and information security. Let's take a brief look at the relationship between them. We all know that where there is code, there will be bugs. If this bug can be tricked by an attacker, then this is an information security problem. If the bug is triggered unintentionally or randomly, it will be considered a functional safety issue. In the past, major OEMs paid more attention to functional safety, often ignoring the importance of information security, because they believe that the relevant DCU is not directly connected to the internet. They think it is difficult to be attacked. But in fact, once a functional safety critical system is attacked, the result will be fatal. Because the safety and security of MCU is so important, there are already many test methods in actual software development, including the following: the code walkthrough. The code walkthroughs are mainly manual code audits. The semi-formal verification and formal verification use mathematical methods to verify code, but this cost is very high. It's rarely used in practice. And in practice, the unit test, interface test, and photo injection test, static code analysis are still the main testing method. Usually, the effective of the test will have several indicators, such as statement coverage, branch coverage, MCDC, and so on. How to avoid software bugs is a concern of both information security and functional safety. I have been doing Linux Android vulnerability mining before, so I'm familiar with EFL, and I consider applying EFL to MCU security testing. So I think coverage-guided fuzzing may be helpful in MCU software security test. And the MCU fuzz is not intended to replace existing testing methods, but to add a testing possibility. After all, there are never enough ways to test, especially in vehicle control systems. Although we all know fuzzing is a very effective way to find software bugs, but there are still many challenges in applying it to the MCU environment. Let's analyze it below and try to solve these challenges. First, let's take NXP S32G as an example, which is currently the most used controller in the vehicle environment. This processor is composed of 3 Cortex-M7 lockstep cores, up to 8 MB SRAM, usually running AUTOSAR or FreeRTOS. There are many challenges to apply MCUFuzz to this environment. First, the physical memory is really very small. 8 MB is clearly not enough. Second, a real-time operating system without an MMU or tags running in one address space. The third, the software developed on MCU rarely use GCC or clone. So some code injection supported by GCC or clone cannot be used here. To sum up, if we want to make a coverage-guarded fuzzing, we will face two major problems: how to trace memory access and how to trace code coverage. We propose a solution. The answer is to use a hardware-assisted debugger. The hardware debugger uses the ARM trace. The trace refers to the process of capturing data that illustrates how the components in a design are operating, executing, and performing. ARM provide many hardware trace abilities. They are called the trace sources, such as the ETM, RTM, HTM, STM. For example, the ETMs provide process-driven trace through an HITB compliant trace port. You can configure the ETM through the call-side APB programming interface. The HTM makes sparse information visible that you can't infer from the ETM. And the ITM and STM are application-driven trace sources that generate trace based on software written to the program interface. We can see that different trace sources are suitable for different scenarios. We are using ETM to help us collect trace data. It is enough for coverage-guarded fuzzing. So let's take a look at the characteristics of ETM in detail. The ETM supports on-chip and off-chip trace modes. Different modes are suitable for different scenarios. In on-chip mode, trace data is temporarily stored in a temporary buffer inside the chip, and the external debugger reads the data in a non-real time. Usually, the internal buffer space is really small. In order to prevent data from being erased, you always need to set the trace filter. To save the buffer space, on-chip trace data is usually compressed, and you need to pass it manually. However, on-chip mode also has benefits. It will be much faster, and it only needs the JTAG interface. Next, the off-chip mode. The off-chip mode exports trace data to an external debug in real time, which requires TPRU or SWO support. The advantage of off-chip is that the external storage buffer is not limited and more data can be stored. Traces can last for a long time, but off-chip requires additional hardware pins and additional hardware debugger. Next, we summarize the characteristic of ETM. ETM is a trace source. It's a part of ARM call-side architecture. It can support instruction and data trace. And it has a characteristic named filter, which can reduce the amount of trace data. And it supports periodic trace data can be generated. Both on-chip and off-chip modes are supported. And the most important, most ARM-based chips supports ETM. Now we know the ARM ETM. We also need to know how to get the ETM data. So we need a tool. Here we use the Trace32 toolset from Loudbar. Trace32 consists of several parts. The first part is the software GUI named PowerView. And on the hardware part, it has Power Debug and Power Trace. The Power Debug is used for detect debugging and also supports on-chip trace. The Power Trace can support off-chip trace, and it has much more high-speed memory to store trace data in real time. Most importantly, the Trace32 almost supports all chips, including ARM Cortex-A, Cortex-R, Cortex-M, but also the Tricore, RISC-V, and so on. Our MCUFuzz tool uses only the cortex-M support. Next, let's take a look at how to use Trace32 to obtain ETM data. This picture is a configuration interface of Trace32 in Trace32. The first part is the trace mode selection. We choose the on-chip trace mode here. The second part is the usage of the trace buffer. Because of the on-chip mode we chose, the trace buffer is very small here. The FRFO mode means that if the trace buffer is full, the older data will be overwritten by the newer data. The third part, auto-ARM and auto-initial. The auto-initial means that every time you restart, the previous trace data will be cleared. This tool, auto-ARM means that the trace will pause and the program is paused, and start as the program starts. The auto-initial and auto-ARM, these two commands are very useful. The first part is the setting part of ETM. Let's look at it in detail. ETM also supports many options. You can see the Loudbar document for details. Here I only introduce one of the most important functions here, the filter. The filter supports code and data filter, and setting trace filter can greatly reduce the amount of trace data. It's very helpful in on-chip mode. And the filter can be done with the filter setting can be done with the following commands. It's very simple, right? Finally, let me show you the coverage interface. The coverage interface can record the data of each trace and analyze it with the source code and form an analysis report. But this function will obviously slow down the fuzzing, so I didn't enable this feature. As I chose to save the trace raw data and start another process to generate coverage report in parallel. Finally, let's talk about the API support of Trace32. All the functions of Trace32 mentioned above can be done through the API, which support languages such as Python or C. After introducing the ETM and Trace32, let me introduce the overall architecture of MCUFuzz. The core agent of MCUFuzz is based on AFL. We add a middle layer between the AFL and the MCU target. This middle layer is responsible for communicating with the debugger and controlling the target to run or pause. At the same time, it will monitor the running status of the MCU, such as collecting crash information. Most importantly, it will be responsible for collecting ETM data and feeding the parsed data into AFL. Then, a fuzzing loop is formed, as the picture shows. Let's summarize the advantage of our MCU fuzz. First is directly realize on any compilers such as GCC, clone, and there is no need to recompile the code or instrument the code. And it's a very smart coverage-guarded fuzzing, and it's not blind. Next, I will show you a specific test demo, which is a real application case in our product development. First, take a look at the composition of this environment. The first part is the Trace32 power debug, which supports on-chip trace and used to control the target MCU and monitor the running status of MCU. And the second part is a USB CAN device. It is used to collect initial seed corpus, and then it is used to send the mutated CAN data to the target device in the fuzzing loop. The third part in our MCU device is an ARM Cortex-M based MCU development board. Let's take a look at the demo video. Pay attention to the trace buffer status. It can be seen that the usage rate is constantly changing because the MCU is constantly suspending pause, collecting ETM data, and re-executing under the control of AFL. You can see that when the usage rate remains constant, the program should encounter an error at this time. In fact, it did trigger a bug in our program. You can see that it only takes less than 2 minutes to find a software bug. But due to the confidential reasons, the details of this bug cannot be shown. The last part, the conclusion. We use the ARM ETM data and the Trace32 power debug. We designed the MCU fuzz to achieve a coverage-guarded fuzzing. And the combination of ETM and the Trace32 is really powerful and helpful. This tool has proven effective in our production environment, and we have found several bugs with this tool. But in addition, the existing MCU fuzz still has a lot to be optimized. First, the fuzzing speed is slow now, and we are trying to improve the fuzzing speed. And the second, we are adapting the MCU fuzz to test more MCU applications, and it's a really time cost hard work. Finally, we are developing off-chip based fuzzing, and we believe that larger storage space should bring more possibilities. And last, I will open source the MCU fuzz on GitHub later, and you can communicate with me at any time. The following is my email and GitHub address. Okay, that's all of my talk. Thank you for listening. Thank you.